Hello and welcome to this video tutorial. Here we're going to look at vectors and kinematics for the AP Physics C course. Please remember to pause or rewind the video as needed. Let's begin. Section 3.1, 3.2, and 3.3. Vectors. Well, vectors are, by definition, quantities with both magnitude and direction. And we can represent vectors four different ways. If we take a look at the image and the picture, the graph over to the right, we can see vector A right here. Now, vector A, the tail of vector A is at the origin 0, 0. The tip of vector A is where we're interested. The tip of vector A happens to be, if we looked at an ordered pair, 1, 2, 3, 4 units in the x direction, 1, 2, 3 units in the y direction, making A four, 3. Now, the actual vector notation can be seen a couple different ways. In textbooks, it can be printed as a bold type, like you see this letter A right here. But in many cases, it's hard for students to make a bold type print on their own paper. So the other way to make a vector notation is draw a half arrow over the top. That indicates the vector notation. So vector A, right, the tip of vector A is at 4, 3. Now, the general way of stating this would be A in the x direction, comma, A in the y direction. In other words, the x component of A, the y component of A. Now, another way we could represent it is in matrix formation or as a column vector. And we can represent that as 4, 3 in a matrix format. Matrix is nothing more than an organized table with rows and columns. And we can see we're representing it with the x component over the y component. The most common way you'll see in university level physics work is in the unit vector notation. The unit vector notation for this would be I plus 3j. Okay, so to generalize this one, it's the x direction component in the I direction plus the y component in the j direction, where I represents the x component and j represents the direction of the y component. Those are the unit vector direction notation. That's called IJK notation. I is in the x direction, j is in the y direction, k is in the z direction, three-dimensionally out of the page. Okay, we can also represent vectors as polar coordinates. Since vectors are things with vectors and magnitude, we can represent it as the radius vector. In this case, it would be 5. Think about that. For 3, using Pythagorean theorem, the magnitude of the length of the vector would be 5. So the magnitude of the vector 5, and it's pointing at an angle of 30-something. Well, what is this angle? This angle turns out to be about 37 degrees, and you can use right triangle trigonometry to figure that out. We'll talk about that one in a moment. So generally speaking, polar coordinates refer to having a radius and a direction vector. Radius and direction, r and theta. This will be very handy when it comes to graphing the position of planets in a planetary orbit when we study Kepler's laws later on down the line. Finding components, magnitude, and direction of vectors. If the angle of a vector is measured relative to the x-axis, then the x component of the vector, we're going to call a sub x, we would find that as the magnitude of the vector a times the cosine of the angle. The x component goes with cosine. And we're going to be referring to the x component in a slightly different way with some vectors. The y component is the magnitude of the vector times the sine of the angle. And we're representing the magnitude of the vector like this. This is the magnitude of the vector. The magnitude is represented with the vector place in absolute value bars. Now, to find this magnitude of A, we would simply use the Pythagorean theorem. Let's take a look at two dimensions first. So if I had a vector pointing, let's say, up and to the right, we'll call it vector A. The x component of vector A, we'll call a sub x, goes to the right. The y component of vector A sub y, points up. And you'll notice that the vector components are nothing more than the legs of a right triangle created by the hypotenuse represented by the magnitude of vector A itself, with the direction angle theta pointing at that respective angle. Now, we know that Pythagorean theorem would be used to represent the relationship between those three sides, yeah? Well, the same is true if we have three dimensions too. So now in vector notation, unit vector notation, the x direction component is represented with an I after it. The y direction is noted with a J after it, and the z direction is noted with a K after it. Okay, so if something's pointing in the negative x direction, it would be negative I. Similarly, if it's pointing downwards in the negative y direction, it's negative J. And if it's pointing, let's say, into the page instead of out of the page, it's negative K. So if I had a vector pointing somewhere off here into this quadrant here that's in the three-dimensional space coming out of the page here, it not only has an x component to the right, a y component up, but it has a k component, a z component, excuse me, that's coming out of the page. And so we could represent this with Pythagorean theorem in three dimensions. X component squared plus y component squared plus z component squared. Okay, now taking a look at this here, we can see that the relationship between theta and your components could also be used with the tangent trig ratio with the y component over the x component. So now if you solve for theta to figure out what theta of that angle is, you simply take the arctangent of it. So theta would be the arctan of the y component over the x component. Okay, now something to note about angles that are, let's say, negative x components, angles that are kind of over in this direction over here, or possibly this direction over here, negative x components require something different. So if the x direction component is negative, okay, then simply add 180 degrees to your direction. Let's take a look at the following example. We have vector A, vector B, and vector C. We want to find the following. We want to find the magnitude of vector A, the magnitude of vector B. We want to find 2 times the magnitude of vector A. This is called a scalar multiple. We want to find the angle at which the vector A is pointing. We want to find the direction that the vector the 2 times vector A is pointing. We want to find the direction, the angle that negative A would be pointing. We want to find the x component of vector C and the y component of vector C. Okay. Okay, let's begin with the first part. Let's find the magnitude of vector A. Now, vector A, you can see we're using IJK notation, is 3 units in the negative x direction and 4 units in the negative y direction. So if you needed to see a visual picture of this, right, vector A is kind of pointing out this way. Okay, so now to find this, the magnitude of vector A, we're going to plug this into Pythagorean theorem. Negative 3 squared plus negative 4 squared is going to equal 5 squared. Square root of that is, of course, 5. Okay, so this is 5 units long. Okay, the magnitude of B. Now, B is a 3-dimensional vector. It's 4 units in the x direction, it's 3 units in the negative y direction, and it's 12 units in the z direction. So we're going to go 4 squared plus negative 3 squared plus 12 squared. Which would be 16 plus 9 plus 144, which gives you 169, square root of which is 13. Now, when you see the notation 2a, that means 2 times the magnitude of a. This is called a scalar multiple. In other words, it's just 2 times whatever the magnitude of a was, which is 2 times, magnitude of a was 5, so 2 times 5 is 10. Okay, now to find theta, the angle of A, the direction of A, we're going to use the arctan equation with the y component over the x component. So the y component was negative 4. Remember, A was negative 3i minus 4j. So the y component is negative 4. The x component is negative 3. Now, when we put this in our calculator and we take the arctan of 4/3, we get 53 degrees. But the reality is we know that's 53 degrees is not correct. 53 degrees points up into quadrant number 1. So you have to add 180 degrees in order to figure out the true direction of this particular vector. So the direction and angle A would be approximately 53 degrees plus the 180, or in other words, 233 degrees. Which direction is twice the magnitude of A pointing? Well, the direction of 2A is still 233 degrees. In other words, it's the same direction as A. Doubling the length does not change the direction of the vector. Okay, what's the direction of negative A? Well, if A is pointing at 230 degrees, this is A, that means negative A points the opposite way. That would be essentially, negative A would be A minus the 180 degrees. Because remember, we had to add 180 degrees in the first place. So the direction of negative A would be approximately 53 degrees. Now, C, vector C, has a magnitude of 4, right? And it's at negative 30 degrees. So negative 30 degrees, right? If you look back at our original picture here, positive angles go counterclockwise, right, around the circle. Negative angles go clockwise around the circle. So positive 30 degrees would be right here. It's positive 30 degrees. Negative 30 degrees would be right here, which is the same as positive 330 degrees. Okay, so now what's the x direction of this? Well, the x direction component would be the magnitude of the vector c, which is 4, times the value of cosine of negative 30. The value of cosine of negative 30 is square root of 3 over 2, which is 2 radical 3, which is approximately 3.5. 3.46, I'll just round it to 3.5. Okay, it's approximation. The y component, similarly, is the vector magnitude of 4, but this time times the sine of negative 30. Right? This was 4 times the cosine of negative 30. Well, the sine of negative 30, right? Sine of 30 is a half, so the sine of negative 30 would be negative 1/2, and negative half of 4 would be negative 2. Plot A and C on the grid. Okay, well, A has a magnitude of 5, points 3 in the negative x direction, 4 in the negative y direction. One, two, three, 1, 2, 3, 4, That would put it exactly right here. There's vector A. Has a magnitude of 5, 3 in the negative x direction, 4 in the negative y direction. Now, vector C, on the other hand, has a magnitude of 4 and an angle of negative 30. So negative 30 would be going clockwise from 0, or remember we said negative 30 is the same as positive 330. Now, the magnitude of 4 would be to the 4th ring. You see the concentric rings here? Here's the first one, the second one, the third one, fourth one, fifth one, and so forth. So we're going to count them up. 1, 2, 3, 4. And so we have a vector that's pointing that far at that negative 30-degree angle. And so that would be vector C right there. Adding and subtracting vectors, multiplying by a scalar. Addition and subtraction of vectors can only be done in rectangular form. To add vectors, simply add the like components. In other words, you'll add the x components of both vectors and the y components of both vectors. To subtract vectors, you simply subtract. X components and subtract y components. To multiply a vector times a scalar, you're going to multiply the scalar by all components of the vector. Okay, notice the vectors over in the diagram to the right. Vector A points up and to the right, specifically 4 units to the right, 3 units up. Vector B points 2 units to the left, 1 unit up, and vector C points 4 units straight down. In this example, we're going to use the diagram to evaluate the following in component form. Okay, then we're going to draw the head to tail addition or the tip to tail addition of vectors, or the tail subtraction of vectors in the grid that is blank down below. Now, if we want to go A plus B, here's how we do it. I'm going to go ahead and zoom in on the picture here. Notice vector A is pointing up and to the right. So what do? We take vector B, which is pointing up and to the left, and any vector can slide anywhere on a two-dimensional plane as long as it is the same length and pointing in the same direction. So I'm just going to take vector B's position and just simply move it to right here. Okay, there's B right there. Now, vector A plus B would be a straight line from start to finish. In other words, right there. Okay, so actually let's go ahead and take this. Let's do this again, but on the diagram below. Okay, now there's actually a couple ways we could do this. Tip to tail method is one way. Parallelogram method, when making a parallelogram out of it, is also another way that it can be done with 2 vectors. Okay, so vector A, again, pointed which way? It pointed 4 units to the right, 3 units up. So here's vector A. Vector B pointed 2 units to the left, 1 unit up. So we're going to put right at the tip of A, we're going to put the tail of vector B, just like that. And vector, the sum, the resultant sum. Now the resultant sum is usually referred to as R, called the resultant vector. It's the result of simply adding, 2 or more vectors. So we'll call it vector R for now. R is the resultant sum of adding vector A and B. And you can see the components of R would be what? 2 units to the right and 4 units going up. Okay. Now, there is another way to do this. I'm going to show this one time over on the original diagram. If you do have 2 vectors, you can also use what is called parallelogram method. Parallelogram method says we take the 2 vectors, put their tails together. Well, their tails are already together. You can see that. And what we do is we create the parallelogram. So I'm gonna copy vector A like this. Move that over here. I'm going to copy vector B. And I'm going to move it right here. And the resultant vector is from where the 2 tails meet to the opposite side of the parallelogram. And you'll notice, ladies and gentlemen, that this is exactly the same as vector R that we have right here. Exactly the same. So when you have 2 vectors that are being added or subtracted, this works for addition or subtraction of vectors. You can use what is called the tip-to-tail method, where you place the tail of the second vector at the head or tip of the first vector. Okay, and then a straight line from start to finish is the resultant vector. Or you can use parallelogram method, where you take the 2 tails, put them together, you complete the remaining other half of the parallelogram, and the resultant vector is from where the 2 tails are connected to the opposite end of the parallelogram. Okay, so let's try A minus B. I'm going to use tip-to-tail method for the remaining examples. So A, remember A went 4 units to the right and 3 units up. So let's draw A. There's A. Okay, now negative B. If B goes this way, B goes this way, from 2 units to the right, 1 unit up. That's B. That means negative B goes exactly the opposite way. Same magnitude, completely opposite in direction. And one thing to note, A minus B is really A plus negative B. So we're going to take that, we're going to move it down here, and our resultant vector, so color in blue, is over here. And it's approximately 6 units to the right and 2 units up. Okay, now what if we want to add A plus B plus C? Well, when you have 3 vectors like this, you have no choice but to use a tip-to-tail method. But you're going to go the tip of A with the tail of B, then you're going to go tip of B with the tail of C. Again, a straight line from start to finish will reveal the resultant vector. So let's take a look. Actually, what would be a good time now is pause the video, attempt this one on your own, and see if it matches up with what I'm about to show you. I'll let you try it. All right, let's see what you were able to get. Starting with vector A, we have an arrow, a vector that is 4 units to the right, 3 units up. That's vector A. At the tip of vector A, I'm going to put the tail of B. B is 2 units to the left, 1 unit up. And C is 4 units straight down. Okay, now remember, the resultant vector is a straight line from start to finish. Start is here, finish is here. The resultant vector is simply that little vector right there pointing 2 units to the right. So in other words, it has an x component, but it has 0 y component. Okay, so now to show this using component addition method, I showed this using the vector geometry. Let's show it a different way too. Vector A, again, is 4i plus 3j. Vector B is negative 2i plus 1j, or 1 in the y direction. Okay, so what would I do? Well, A plus B would just be the sum of that. Right? I'm going to add my like components. 4 plus negative 2 is 2 in the x direction. And then if I go 3 plus 1, I get 4 in the y direction, which is exactly what we have here. 2 in the x direction, 4 in the y direction. Okay, if we were to look at this one here, A minus B, okay, would be, again, we have 4i plus 3j minus negative 2i plus j. Okay, add the like components. And we have 4 minus a minus 2 would be 6 in the x direction. And 3 minus the 1 would be 2 in the y direction. So 6i plus 2j. And you can see that matches the picture we had before, 6 in the x direction, 2 in the y direction. Okay, and finally, for adding A plus B plus C, that's going to be 4i plus 3j plus negative 2i plus 1j plus 0i minus 4j. Okay, let me pause on the vector C for a second. Notice vector C is only going in the y direction, therefore it has no x component. It's wise to put a 0 placeholder with anything that doesn't have a component. It just kind of keeps it organized for you. Okay, add them up. The x component would be 4 minus 2, or 2 in the x direction. Then you have 3 plus 1 is 4, minus 4 is 0, plus 0j, which would just simply be 2 in the x direction. And you can see that's confirmed with our picture right here, a resultant vector 2 units in the x direction. 2 times b. Okay, now vector b, if you recall, was negative 2i plus j. So 2 times b would be 2 times negative 2i plus j, which would be negative 4i plus 2j. In other words, it doesn't change the direction, it just makes it twice as long. So, in other words, this is b right here, so 2b would just be twice as long down to here. So so 2b would be over here. Negative a, well, if a, so remember vector a is 4 units in the x direction, 4i, plus 3 units in the y direction, that's 3j. So if we do negative a, that would be negative 4i plus 3j, which would be negative 4i minus 3j, which basically just takes this vector that's pointing up and to the right and flops it 180 degrees the other way down and to the left. And there's negative a. Okay, and then let's see, a plus 2b plus c. Okay, so we're going to go 4i plus 3j and 2b. Now remember what 2b was. We just did this over here. 2b is going to be negative 4i plus 2j plus c, which was 0i minus 4j. Okay, add your x components. Negative 4 is 0, plus 0 is 0. So far I have 0i plus, now add your y components. 3 plus 2 is 5, minus 4 is 1. In other words, we get 1j, or 1 unit, in the y direction, or we'll just call it j. There's no reason to write the 1 in there. Okay, let's represent that. Let's figure it out. So a goes 4 units over, 3 units up. 2b is going to go 4 units left, 2 units up. So there's a. At the tip of a, we put 2b. And at the tip of 2b, we put c. C goes 4 units straight down. 4 units straight down would put it right here. Which means, if you look, straight line from start to finish is this small little vector right here, which is our resultant vector, exactly 1 unit in the y direction. Let's take a moment to summarize the properties of vectors. Vector addition is commutative and associative. That means whichever way you choose to add the vectors, vector A plus vector B gives you the same result as adding A to B as it is B to A. Associative means if I take 2 vectors and add them, if I add A and B and add the sum of A and B to C, that would be the same as adding A to the sum of B and C. Now, vector subtraction is anti-commutative. That means A minus B is the negative of B minus A. Now, if vector A is multiplied by scalar k, and the magnitude of vector A is multiplied by the absolute value of scalar k. And then finally, if vector A is multiplied by scalar k, the direction of A is either the same, direction of B, angle B, theta B is the same as A, if k is positive, but if k is negative, then we need to either add or subtract 180 degrees to figure out the direction of angle B. Derivatives. Differentiation is a mathematical operation that acts on a function y equals f of x. The result is called the derivative of f, and it is also known as y prime. Sometimes it's noted with a little dot over. Usually it's noted as a little apostrophe afterwards, or f prime of x. The derivative gives the slope of the function f of x at the given value of x. Okay, for us, it represents the instantaneous rate of change of the function. Okay, more to come on this soon. It takes exactly 2 points to establish a line and calculate a slope. To find a slope at any single point, xy, on the function y of f of x, we choose another point, x plus delta x and y plus delta y. Now, in an actual calculus class, we define the derivative of any function of x as the limit, delta x goes to 0, of f of x plus delta x minus f of x all over delta x. This is known as the difference quotient. Now, in a physics class, we don't really need to use this. We will instead employ many calculus shortcuts along the way. So let me show you what they are. The first one is constant rule. If f of x equals c, a constant, so if our function is a constant, then our derivative of a constant is 0. Power rule. If f of x equals cx to the n power, where c and n are constants and n is not negative, not 0, then we use the following. You take the exponent, you bring it down, multiply it times c, and then subtract 1 from the exponent. So we would write that as f prime of x is equal to c n x to the n minus 1 power. Now, in terms of adding and subtracting derivatives, well, that's just adding and subtracting the terms. So if y equals f of x plus or minus g of x, then y prime, which is the derivative of y, would be equal to f prime of x plus or minus g prime of x. Constant multiple rule states that if we have a constant c multiplied times our function f of x, again, c is a constant, then y prime is equal to c times the derivative f prime of x. Let us take a moment to remind ourselves of the derivatives of various trig functions. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent x is secant squared x. Some of the more exotic ones that may or may not show up, the derivative of secant x would be secant x times tangent x. The derivative of cosecant x would be negative cosecant x times cotangent x. And the derivative of cotangent x would be negative cosecant squared x. As far as the derivative of your inverse trig functions, the derivative of arcsine of x would be 1 over the square root of 1 minus x squared. The derivative of arccosine would be negative 1 over the square root of 1 minus x squared. And the derivative of tangent would be 1 over x squared plus 1. Those bottom three rarely show up in AP Physics, if ever, but it's good for enrichment purposes to know them. The derivative of natural log of x is 1 over x. And the derivative of e to the power of x is e to the x. Let's take a look at the following examples. First one, 4x to the third power. Well, f prime of x, we're going to use general power rule because we have a polynomial function. So this would be, bring the 3 down front, so 3 times 4x to the 3 minus 1, or 12x squared. Okay, now in this next example, this is a polynomial function with 5 terms. The way we do this is we take the derivative of each 5 terms independently and just simply add or subtract the terms. So f prime of x would be the derivative of x to the fourth. We bring the exponent down and then subtract 1 from the exponent. So it would be 4x to the third power plus, you're going to bring the exponent down, multiply it times 2. We get 6x to the second power. So always subtract 1 from the exponent. Okay, minus 8 times x to the first power. Plus, now what about something like this? Well, 3x is really 3x to the first power, right? So if I bring this down, this would be 3 times 1, x to the 1 minus 1, which is 0. And 3x to the 0 power is just 3. So when you're deriving, let's say, something x with respect to x, then all you're going to get is the constant in front. So that's something to note. The derivative of 3x would just be 3. And the derivative of any constant would be 0. Okay. Now, in this next example, we have f of x equals square root of x plus 4 times the cube root of x minus 2 over x plus 1 over 3x squared. Kind of looks hard at first, but really the key is rewrite any rational expression as a negative exponent, and write any square or root, square root, cube root, fourth root, whatever, write any root as a rational exponent. Okay, so just to remind yourselves about your rules for exponents. Number 1, x to the negative n is the same as 1 over x to the n power. Okay, so I can essentially take a fraction, any value that's down here, I can rewrite it as a negative exponent like this. That's one rule that we're going to employ in just a minute here, but we're going to do it in the following way. Okay, 1 over x to the n power, we're going to rewrite it as x to the negative n power. And then also a radical, so if I have if the nth root of x to the m power, we're going to rewrite that as a rational exponent of x to the m over n. Okay, so we're going to use those two right now. So first things first, rewrite f of x. Don't take the derivative yet. So x, this is x to the first power, right? And it's a square root, so it's a second root. So we'd write the square root of x as x to the 1/2 power plus 4. Now this is the cube root of x, so x to the first power, but you're taking the cube root of it. So it's 4x to the 1/3 power minus 2. Now this is 2 over x to the first power, so I'm going to bring that up. And when I bring it up, it becomes 2x to the negative 1 plus 1/3. The 3 stays down there, but I can bring the variable up. And when I bring the variable up, the exponent becomes negative. So 1/3 x to the negative 2 power. So that's our first step, is just rewrite everything, okay? Next step, general power rule on each term. Bring the exponent down, subtract 1 from the exponent. So it's going to be 1/2 x to the 1/2 minus 1 plus 1/3 times 4 x to the 1/3 minus 1 minus, now you're going to bring this one out in front here too. So negative 1 times 2 would be positive 2x to the negative 1 minus 1. Again, always subtracting 1 from our exponent, right? And then finally, negative 2 times 1/3 x to the negative 2 minus 1. Okay, let's clean this up. F prime of x would be 1/2 x. Now 1/2 minus 1 would be negative 1/2 power. Plus 1/3 times 4 would be 4/3 x. Now 1/3 minus 1 would be negative 2/3. Okay, plus 2x to the negative 1 minus 1 would be negative 2. And then finally, negative 2 times 1/3 would be minus 2/3 x to the negative 3. Okay, now all I'm going to do is just simply rewrite all those negative exponents back as positive exponents, and we have a nice simplified version of our derivative. So it would be 1/2 x to the 1/2 power, which is the square root of x, so 1 over the square root of x, plus 4 over 3 times the cube root of x squared. Plus 2 over x squared minus 2 over 3 x cubed. Okay, so now taking a look at our trig ones here, just take the derivative of each trig one independently, each trig function. So the derivative of sine is cosine, so this would be 6 times cosine of x minus 2. Now the derivative of cosine would be negative sine of x. So just kind of cleaning this up a little bit, we would get 6 cosine of x minus minus is a plus 2 sine of x. Product and quotient rule. Although product and quotient rule are not a major portion, in fact, they're a pretty rare portion of AP Physics, we're going to review them just for enrichment's sake. Let f of x be the product of two different functions, u of x and v of x. In other words, if f of x is u of x times v of x, then the derivative of f is found as u prime times v plus u times v prime. Now let's say you have several products. Let's look at the example of t of x times u of x times v of x times w of x. Well, that's going to be t prime times u vw plus t times u prime plus times v times w plus t times u times v prime times w plus t uv times w prime. Now consider the situation where f of x is the quotient of the two functions u of x and v of x. In other words, f of x equals u of x divided by v of x. The derivative is given by f of x equals u prime v minus, not plus this time, u v prime, but then it is divided by v squared. Again, product and quotient rule are not something that are frequently used. We might use quotient rule one time in the entire course. Chain rule, on the other hand, is something we have to use quite often. Let y be the function of f, which is itself a function of g. In other words, f of g of x. That is a composite function where g of x is inside f of x. Then the derivative of y would be the derivative of f, hold the g function fixed inside g of x, times the derivative of that inside g of x function. So now what if you have a whole bunch of composite functions, say f of g of h of k of x? Well, you just have 4 different chains. F prime holding g of k of h of x fixed times g prime of holding h of k of x fixed times h prime holding k of x fixed times, finally, the derivative of the inside function k. Let's take a look at a few examples that would use this. Y equals sine of x times ln of x. Well, sine of x is cosine, so remember this is a product here, so product rule, f prime times g is going to be f prime g plus f g prime. So there's our f function, there's our g function. So we're going to go the derivative of sine of x first, which would be cosine of x. And I like to put my derivatives in brackets and then my regular f and g functions in parentheses, just to differentiate what I took the derivative of versus what I did not. So this would be cosine of x times natural log of x, plus, now it's f times g prime. So we're going to hold the f function fixed of sine of x, notice I'm putting that in parentheses, times the derivative of ln of x, which is 1 over x. Okay, so just kind of cleaning it up real quick, we get cosine of x times natural log of x plus, and then if you just multiply those two together, it would be sine of x over x. Okay, so we have, this time, 3 products. We have f times g times, we'll call this h, right? So y prime would be what? F prime times gh plus f times g prime times h plus fg times h prime. Okay, let's do this one step at a time. Y prime, going to take the derivative of f, so that would be 2x, put that in brackets, times cosine x times the arc sine of x. Okay, plus the next part. Okay, so we're going to bracket off f right here. So f would be x squared times the derivative of cosine, which would be negative sine, times the arc sine of x, plus the final one, which we do over here, we're going to parenthesis off x squared and cosine. But this time we're going to derive arc sine. And the derivative of arc sine, in case you forgot, was 1 over the square root of 1 minus x squared. Okay, so just to kind of clean that up a little bit, y prime would equal 2x cosine of x times the arcsine of x plus, now since there's a negative right there, that plus really is a minus, so minus x squared sine of x times arcsine of x plus x squared cosine of x over the square root of 1 minus x squared. Kind of a big one. Y equals sine of x over cosine of x. Well, this is clearly a quotient, so we're going to use quotient rule. Quotient rule, in case you forgot, the derivative of a quotient, we'll want to call this f over g, is going to be f prime g minus, not plus this time, f times g prime, and then divided by g squared. I'm going to call this the f function. I'm going to call this the g function. So y prime would be, bracket off the derivative of f, so the derivative of sine would be cosine, times the original g function, cosine, minus, not plus this time, the original f function, which was sine of x, times the original derivative of the cosine function, which is negative sine of x, all divided by cosine x squared. Let's clean this up a little bit. Okay, so just cleaning this up a little bit. Y prime would be cosine squared x plus sine squared x over cosine squared x. So to write cosine x quantity squared, you could write it cosine squared x. The top is a Pythagorean identity. You see, if this is x, and this is y, and y is equal to cosine of x equal to cosine of x, and y is equal to sine of x, then Pythagorean theorem would say that this hypotenuse is going to be the sum of x squared and y squared. And that is going to be, this is all part of the unit circle, so this is a unit vector of 1. Therefore, cosine squared plus sine squared is 1 over cosine squared x, and this is called a reciprocal identity. The reciprocal of cosine would be secant. So 1 over cosine squared x would be secant squared x. And something to note about this one, secant squared x is actually the derivative with respect to x of tangent of x. And if you look at the original function, sine over cosine is tangent of x. So yes, we had a shortcut, but I wasn't going to show you that shortcut right away. Sine of x squared. Okay, this one looks like a chain rule one to us because we have an outside function of sine and an inside function of x squared. So what we're going to do is we're going to go y prime. The derivative of sine is cosine. Hold the inside function fixed times the derivative of the inside function, which would be 2x. We're going to take this, multiply it times the outside, and we get y prime is equal to 2x cosine x squared. Now, the outside function is some quantity squared, and the inside function is sine of x. Still chain rule. So the outside function is the squared function on the outside. So that would be general power rule. We bring the 2 down and then subtract 1 from the exponent, right? So we're going to go 2 times sine of x to the 2 minus 1 times the derivative of sine of x, which would be cosine of x. And we would get 2 times sine of x times cosine of x. Y equals sine of ln of arctan of x. Okay, so we have a few chains going on here. First one, y prime, we're going to take the derivative of sine, which is cosine, holding the inside functions fixed, so the natural log of arctan of x times, now we're going to multiply by the derivative of natural log now we're going to multiply this times the derivative of the inside function. So we took the cosine, the derivative of sine was cosine, hold the inside function fixed, which is natural log of arctan of x, times the derivative of the next inside function, which is natural log. Now the derivative of natural log is 1 over x. Now x, or I should say 1 over u, we're going to let u be this other inside term, natural log of x. So it's 1 over u, which is arctan of x, times, finally, the derivative of the last inside function, which was the derivative of the arctan of x, which was 1 over x squared plus 1. And I would say don't worry about trying to rewrite or simplify that one. Just let's leave it as is. Now let's take a look at second derivative. The second derivative of the function f of x, noted y prime or d squared y dx squared, means the second derivative with respect to, in this case, x. And it would just be the derivative of the derivative. So if we take the derivative of x and then take the derivative one more time, we have the second derivative. So let's take a look at this example. Find the second derivative of e to the x times sine of x. Well, this is going to be a product rule problem because you have two functions multiplied times each other. I'm going to call this f, I'm going to call this g. So y prime, so remember f prime times g, f times g would be f times prime g plus f times g prime. So f prime, the derivative of e to the x is the same, it's e to the x, doesn't change, times the original g, which was sine of x, plus e to the x times the derivative of sine, which is cosine. Okay, so we got this part. Okay, now what we're going to do is we're going to take the derivative of each derivative. So y prime is e to the x sine of x plus e to the x cosine of x. And again, I'm just going to treat this as like an f and a g. I'm going to treat this like another f and another g. Okay, to do product rule twice, essentially. So y prime, or I could factor out an e to the x and then the remaining sine plus cosine and treat that as one function too. I have multiple ways of doing this. Okay, I'm going to choose to break it up like this. So in the first part of the function, e to the x times sine of the x, we have the derivative of e to the x, which is e to the x times the original g, which is sine, plus the original f, which is e to the x times the derivative of cosine, which is negative sine. Okay, so we've got that part. Okay. Whoops, sorry, let me back that up. Yeah, my eyes got a little bit moved over. Sorry, I need to focus on just this term only. Okay, so the derivative of e to the x times sine plus the original f, which is e to the x, times the derivative of sine, excuse me, not cosine, which would be the derivative of sine is cosine. Okay, and then we're going to go, all of this is just the derivative of that. Okay, now plus, now we're going to take the derivative of that part. Okay, so we're going to go, again, original f function, or excuse me, derivative of the f function would be derivative of e to the x, which is e to the x, times the original g, which is cosine, plus the original f function, which is e to the x, times the derivative of cosine, which is negative sine. Okay. Now, we have 4 terms here, a bunch of e to the x, sine of x, e to the x, cosine of x. So what I'm going to do to clean this up, I'm going to clean up each term and then see if we have any like terms in here. So we have e to the x sine of x plus e to the x cosine of x plus e to the x cosine of x. You guys can already see there's like terms right there. And then minus, because you got the minus right there, minus e to the x sine of x. Well, e to the x sine of x minus e to the x sine of x means those two cancel, and so your second derivative would be 2 e to the x cosine of x. Okay, so something to note about the application of the second derivative. So if the first derivative is positive, right, then the function will be sloping upwards, right? If it's negative, it'll be sloping downwards. Again, if the first derivative is positive, it'll be sloping upwards. If the second derivative is negative, that part of the function is concave down. If the second derivative is positive, that part of the function is concave up. And this little chart here does a great job of summarizing that for each quadrant. Finding extrema, maximums and minimums. Well, the critical point represents the point where the derivative, or f prime of x, equals 0. In other words, if you look at the function, this represents, if f prime of x, the derivative, represents the slope, right, and where the slope equals 0, that means a flat line. So you can see minimum, maximum. Okay, now an absolute minimum and maximum, of course, is where it's absolutely the greatest and smallest. Local minimum maximum is a place where your f of x values are going to be higher than everywhere around it, and your local minimum is the point where your f of x values are going to be lower than every value around it. The point of inflection, this point right here, is the point where you change concavity. Notice this is where we go from concave down to concave up. Okay, now in calculus, the critical point can also be observed in some places where the derivative is undefined too, but we're not going to focus on that. Derivatives of vector functions. To take the derivative of vector functions, simply take the derivative of its components. So treat I, j, and a as if they were constants. Okay, let's take a look at this last example. Let x equal 3t minus 1i plus 2t squared minus 4tj minus 6k. Find x prime, the first derivative, and x double prime, the second derivative. Okay, so x prime all you have to do is just simply derive, right, each of the components. So the first one, the derivative of 3t minus 1 with respect to t would just be, the derivative of 3t would just be 3, right? And the derivative of 1 is 0. So we have basically 3, and then the I. It's a, you remember, treated like constant, so they just go along for the ride, right? Constant multiple. And then plus the derivative of 2t squared is 4t, right? Minus the derivative of 4t would be 4. So we have plus 4t minus 4 in the j direction. And notice that the constant in front of k is a minus 6. So that would be the derivative of 6 is 0. So that part essentially just drops out. The second derivative of this, the derivative of 3 in the I direction drops out, and the derivative of 4t minus 4 is just 4. So the second derivative would be 4j. Review of 1D kinematics, section 2.1, 2.2, 2.3. Let's review some of the older kinematic equations when we would use them. So our basic constant velocity equation tells us that the position you're traveling, the position that you're at, is going to be equal to your initial position, wherever it is, to start with at time equals 0, plus your constant velocity times time. Typically, you would see this as velocity equals position over time, but this is another way to write it. Sorry, change in position over time. Subtract this over to the other side and divide by t, and that's how you get the same result. Now, I'm going to say, or we could write it this way, because writing it in this form puts it in a slope-intercept form that becomes very recognizable in terms of the slope, right, of a position versus time graph is your velocity, and the y-intercept is your initial position. Now, constant acceleration equations, one particular constant acceleration equation, position as a function of time. And we can see x equals x naught plus v naught times t plus 1/2 at squared, or, again, if we wrote it, y equals a t squared plus b times t plus c. In other words, quadratic function. Now, constant acceleration equation without time, well, that would be v squared equals v naught squared plus 2ax. Again, writing it like this, we can see that if we were to plot y equals mx plus b, the slope would be 2 times the acceleration, okay, if we were plotting velocity squared versus your position, and the y-intercept would be your initial velocity squared. Average velocity equals delta x over t. And average acceleration equals delta v over t. Now, if we looked at this one more time, we would see that average acceleration for, if the acceleration is the same and constant, then average acceleration is constant acceleration. They're the same thing. And so I would rewrite it as acceleration equals v minus v naught over t. Then I would multiply both sides by t, and I get a times t equals v minus v naught. And if we take a second to add v naught to both sides, we have another expression, and that would be, I'll say, or v equals v naught plus a times t. This one gets used the most. Now, instantaneous velocity, hey, this is where our new relationships come in. Instantaneous velocity represents the slope of the tangent line at the curve at that particular time. Well, what does slope represent? Well, it's the derivative. So the derivative of your position function with respect to time is our instantaneous velocity, and our instantaneous acceleration would be the derivative of the velocity function with respect to time, or the second derivative of the position function. At this point, we're going to move on to page 10, projectile motion, and we will be working on the example problems together in class. Projectile motion, section 3.4. Projectile motion occurs when a particle is in free fall. The only force acting on it is gravity. There's only acceleration in the negative y direction, and the motion in the x direction is constant velocity. So horizontally speaking, in the x direction, if we're moving with constant velocity, then we would expect to use a constant velocity equation. Remember the equation from above, x equals v times t plus x naught? Well, we're going to assume x naught equals 0. We're starting it at 0. And this represents the initial velocity in the x direction. Now, if we take care of our components, our initial velocity in the x direction is going to be v naught cosine of the angle. Let's say we have an object launched at some angle. This is v naught x. This is v naught y. This is angle theta. V naught x is the adjacent side of the triangle, and that would be the hypotenuse, v naught, times the cosine of the angle. V naught y is the opposite side of the triangle, and opposite always goes with sine, so v naught sine of the angle. And we'll need both of those. We can see the vertical equation is just a vertical form of the horizontal equation that we wrote down earlier. Okay, a couple differences, obviously. X in place of y. X naught in place of y naught. Right? Y naught in place of x naught. V naught y instead of v naught, so we're giving a very specific direction. It's v naught in the y direction. And instead of positive a, we're doing minus g. And again, v naught y is v naught sine theta. Okay, now velocity is a function of time. We have vx equals v naught x plus axt, but acceleration in the x direction is 0. There is no horizontal acceleration. So what does that tell us? Velocity is constant. The initial velocity in the x direction is any velocity in the x direction. Vy, on the other hand, is equal to v naught y minus gt. Acceleration in the x direction is 0. Acceleration in the y direction is equal to a negative g. At this time, make sure you pause and rewind the video if you need to obtain your thorough notes. I hope you found this helpful. We will go over the examples in class together.